We're going to call the class to order. So today we have our class on RAG model. Okay, so I think we're going to start with the usual, which is we have Kahoot. So I'll ask our presenter for Kahoot to run the Kahoot.
The first question is, what is true about retrieval in the retrieve then direct architecture? Basically for this, in this architecture, the retrieval is used to scope out a smaller scope of articles that can be ranked afterwards for efficiency. So that's why I target recall prediction. You want to just get all the documents that we know are generally in the final hits. It also is meant to just be a filter, so like reduce the scope for the ranker to be ranked. So it doesn't give out efficiency for prediction because prediction is handled by the ranker, and it's also not the final ranking. So yeah, that's the first question. So very bold. All right, let's go to the next question. So there were 3 ways to rank documents. What does it mean to rank? What's one? three ways here are the different ways that they rank documents. So first it was point wise, where you give each document a score. When we compare two documents, it's usually better that is pairwise comparison. And then there's also list-wise comparison to generate ranking from the entire list of documents. Yeah. So we still have Y on top for everyone's using a single letter. Alright, so I'm going to go to the next question. So this is the third question. What is true about traditional and digital LPR learning program? This is also a multi-select question. So remember that a newer LPR uses like semantic similarity. So because like instead of exact matching, which is what traditional LPR uses, it uses that to get the features. And yeah, so the neural LPR methods are not only representative based because we have interaction based ones like match pyramid and DRMM or transformer based ones. And then for the traditional LPR also allow interaction based, but we still the thing is that you need to make it with feature engineering ourselves. There are a few examples in the slides if you're going on. So that's the third question. All right. So we are halfway through the quiz. We have 3 more questions to go. So I don't know if this is the correct verbiage, but basically, what for the contributors, what is the main thing that we talk about? So this is mentioned how the contributors work for the project. So most of all that got this right. So basically it's contrastive learning because contrasting between similar and dissimilar things. The rest are all just other things that I put in there. Yeah. So I got the correct mostly. Again, going quite well. Right, the penultimate question. So what are the general attributes of a cross-encoder model? Again, it's a multi-select. So remember there were 2 models that were covered basically of the bi-encoder and the cross-encoder models. Basically, cross-encoders are more expensive because they are interaction-based, they complicate. They basically process both inputs with a single pass. So that's the general attribute of a cross-encoder model. And to end it off, we have 1 more question, but before that, we look at the scoreboard. Look pretty good. All right, the final question is, what are possible motivations to use an LLM? Yeah, so basically, I think this can be LLMs are generally good because you can use them zero shot. You can use them without using labeled data, and it also handles the query formulation expansion without passing implement like rule-based systems. But it is definitely not cheaper because LLM query can be expensive depending on what you use, and also LLMs are like a bit of a black box, so it's harder to monitor than if let's say you build your own. So to finish off, that is our final podium. So congrats to everyone that did well. Thank you.
Thanks so much for running Kahoot. We'll have another week next week or today's lecture. Okay, so today we have Mingyu, Nura, Zak, Ruiwen, Barid, and Sahej giving the talk today. Is our first presenter online or?
Yeah, I'm here.
Okay, I'm gonna stop the screen share and you can.
Okay. Okay. Hi everyone. Thank you for attending our presentation on lag models. I'm Mingyu Lee, who is the first presenter in this section. And this presentation is prepared with Nura and Zak and Ruiwen and Barid and Sahej together. And let's start. Let's start this presentation. In the world of the AI, large language models have shown incredible capa capability, but what happens when their built-in knowledge isn't enough? Uh, where came in. I will guiding you through this first section of sorry of section on overview of lag paradigm, and we will explore the fundamental question of why lag is so crucial and how it has evolved from a simple concept into sophisticated and powerful architecture. So let's start with sorry. So let's start with the core motivation. The a H1 visa example on the slide to the left to specifically illustrate the three key limitations of standard large language models. First one is latency. The user asks about the visa fee for the year 2026, and now imagine on large language model trained on date up to 2023. If US government announced a new fee structure in 2024 or 2025, the large language model would have no knowledge of it. This is why it provides generic answer you see on the slide, such, such as an H-1B petition usually include a base filing fee, a training fee, a fraud prevention, etc. Which means it falling back on all general information because it lacked awareness of specific up-to-date rules for 2026. The information is not just missing, and it is also outdated. The second one is verifiability. Looking at the model's response, an H-1B petition usually include a base filing fee and training fee and fraud prevention. And this sounds plausible, but where did it comes from? Is this from the official US immigration website or just the model summarized on unverifiable blog post from the years ago? So because of all of this knowledge is backed into its parameters, we cannot easily trace the source to verify its accuracy. Third one is reasoning depth. The user question is how much is the fee, and they asked for specific total cost. But however, LLM response only lists the components of the fee. It failed to perform the necessary multi-step reasoning. So they just find the cost of each individual component applicable in 2026 and then to calculate final sum. These three challenges are precisely what lag is designed to solve, and log act as bridge to integrate external and non-parametric knowledge. So the journey of log is one of the continuous improvement to solve this three problem. Today we can broadly categorize this evolution into three key stage. First one is knife log, which we can see in the left side. The most straightforward implement, as we will see, is simplistic, is both strength and weakness. Next is advanced log, which is overcome this knives log's limitation, and this field developed and called as advanced log. This stage introduced a crucial pre-processing process and post-processing steps to improve both retrieval and generation quality of the knife log. Finally, we can see in the right side, which is a modular log, which represents the current state of art method, and this paradigm viewed log not as a rigid pipeline, but as flexible and framework of changeable components, allowing for highly customized and powerful systems. Okay, and then let's start with the foundation knife log. In its essence, this is a simple two-stage process. We can think of it as a standard open book example on log. First, we have the retriever. When a user asks a question, the retriever's job is to search through the external knowledge base and found the documents that seems relevant. In our examples, it found a document about a new $100 grand payment in 2026 and another about the 2024 fees and one irrelevant documents. And second, we have the generator as shown in the right side, which is normally used using a large language model. The documents found by retriever are packed together with the original user's question into the prompt, and the large language model then read this combined information or prompts and generate the final response at the right side. This process have the ground the large language model's answers in external reality. However, this simple approach can fail in several ways. First are retrieval challenges. The quality of the final answer depends entirely on the quality of retrieved documents. As we can see in the figure, the retriever might pull the irrelevant documents, which can confuse and generate and read to low quality answer. And second, we can face generation difficulty. Even with the relevant documents, the large language model can still make mistakes. If the information is complex and contradictory, the model might misinterpret it, and they can read and this can lead to hallucinate response, where the model generates a confident sounding response but factually incorrect answer, like a one $50,000 fee shown in the right side, which is appear in the none of the source documents. Finally, there are augmentation hurdles. This refers to the challenge of smoothly integrating the information. A knife approach might simply cause the large language models repeat the facts from the documents, leading to the redundant and unnatural response, like repeating the response like $100,000 fee twice. To address this shortcoming, advanced lag introduced more sophisticated techniques before and after retrieval steps. First is the pre-retrieval process. Instead of using the user query directly, we can refine it with a powerful technique such as query decomposition or query rewriting. Query decomposition is where the complex question is broken down into the several simple sub-questions. For instance, for our H1B examples, we can generate separate queries for fee before 2026, a new payment in the 10 year, and the total cost. This targeted approach with too much and more accurate document retrieval. After retrieval, we have a post-retrieval process in this advanced lag paradigm. This is where we filter out the noise, and the key component here is a re-ranker. This is also replaced by another module such as summarizer or something else. And re-ranker's job is to take the initial list of documents and resort them based on their actual relevance. This ensures that the most important information is prioritized and passed to the large language model. This curated context allows the generator to produce much more precise and correct response, like the final answer of over 133,000. This brings us the final and most flexible paradigm. Last one, modular lag. Modular lag moves away from the fixed pipeline and treats the entire process as a collection of specialized modules that can be combined in various ways, which we can see in the right side. We have modules for searching, rewriting, and retrieving, re-ranking, and routing. For instance, knive lag is just retrieve modules followed by read modules, and advanced lag is one type of modular lag, might added rewriter module in between them. But modular lag allows for far more complex workflows like iter-regen example, where we can create a loop to iteratively refine the result. And this adaptability make modular lag incredibly powerful for tackling complex multi-step listening tasks. And this overview is conclude our high-level tower of lag paradigms. We've seen how lag addressed key large language model limitation, and this evolved from simple concept to highly flexible framework. And this lag paradigm have also three main pillar. First one is retrieval, and second one is augmentation, and third one is generation. And this is also introduced by three others presenter after this simple overview. Thank you for listening my presentation. If you have any question, feel free to ask me.
Okay, let's thank our speaker. There's at least one question by Rishab as discussion panelist on Slack. You're welcome to participate. So Nura is in the classroom. We can go to that section by Nura, since this is more of an introduction and a recap of what I think all of us should be pretty familiar with. Okay, thanks Mingyu for presenting. So stop your screen share.
Okay.
So I'm gonna talk about part of RAG. So this is an overview of like what I'm going to cover today. Outside. Okay, so yeah, so like basically data structures, like retrieving data is the most important part of that retrieval, right? So there are like 4 types of like different data structures that we have. So first one being like unstructured data. This is the most common data type for RAG that is being used today. Then for semi-structured, it's usually like PS and shit, which contains like text and tables. So the problem with this is that tables, like splitting tables, is difficult, and this leads to like data corruption. Yeah, and incorporating similarity searches is difficult when it comes to semi-structured data. Structured data is the easiest to work with. But yeah, it requires a lot of effort to like maintain and build structured data sets. And finally, nowadays we have like LLM generated content where like instead of doing the whole process, you just replace it with an LLM generator itself. So these are like the basic data structures that we have today for our retrievers. Another important concept when it comes to retrieval is the granularity. So we have like coarse-grained retrieval and fine-grained retrieval. Coarse-grained retrieval is more like to have like more information when you retrieve. So like that contains more context. So it's good in a way that you'll be able to gain more context, but a fine-grained focus more on like refined information. And but the problem with this is that there's higher retrieval overhead. So like you need to search more to cover like all the queries and they cover all the information that queries can retrieve. An example of like fine-grained retrieval is DenseX. So they propose this concept of having propositions, where like a single statement is broken down to like contain one fact. For example, like Albert Einstein was born in Germany in 1879, would just Albert Einstein is born in Germany. This is like one statement would contain only like one fact. The idea behind this is that you would feed like only like precise information into the model, so that you don't give it like a lot that it has to like process, and it would reduce noise. Yeah, so like text data is usually broken up into like this token phase sentence. So like, what do you guys think? Like, what do you guys think is like fine-grained retrieval and like coarse-grained retrieval in this diagram? Like, which part of this would be like coarse-grained and fine-grained?
Come on, guys. So, for example, with the for text part, would that be fine-grained retrieval, and the second point there would be coarse?
No.
Oh.
Not like that.
That's my maybe perhaps
Yeah, this might be documents might be coarse-grained and then total fine-grained.
Yeah. Yeah, similarly for knowledge graph, like entity triplet, that those would be like fine-grained, whereas like a subgraph would be like coarse-grained. Yeah, so that's the idea behind that. Okay, so now we talked about like how important it is to retrieve like right information. The next thing is like, okay, if you have retrieved right information, but like is like one query enough to retrieve all the information that's required for the like query? Okay, so that's where this concept of RAG distribution comes in, where we believe that like a single query is too ambiguous to retrieve the right information. So the idea behind RAG distribution is that you take one query and you generate like multiple queries from it. So for example, like this query, tell me about English micro. It's very general, but this would be taken down and split into like 3 questions, like what is it, how does it work, and so on. So this way we're able to retrieve like more fine-grained information from it. And how it works is like the first part would be to split the query into like sub queries. And then for each query, you receive like a set of documents. And obviously these documents would be ranked, right? And you re-rank all the documents that you retrieve with the order of like which document appeared more often, and which documents had like a higher rank. So like this is how it's re-ranked, right? RRF. So the idea behind RRF is to like just give higher weight to like documents that appear more or like has a higher rank. So yeah, so this is just to ensure that like documents that are highly ranked by multiple retrievers are favored in the final rank. So here like you can see that in this diagram. So in this diagram, this query would retrieve like, let's say like 2 documents, and the same document would be retrieved by like this query as well, because that means that document is like more relevant. So when you do RRF, these documents that are retrieved more often would be given more priority. They would have a higher rank. Yeah, and they have like a case moving factor to ensure like we don't have any biases. Okay, so this is a query that they fed to the RAG fusion, and like we are comparing it against forums that was available. So like it's asking for a rating for this product, let's say. So that is split into three, four queries, and that is fed. So this way the bot is able to retrieve the reason why it has given this rating, and like all of this relevant information. Whereas form solution just like talks about the rating. So the idea is that we are able to like generate a lot of like important information with the help of like practice. And here is like where like a situation where like there wasn't enough data. So even with having multiple queries to search for the relevant documents, here the bot was not able to retrieve the most important information, which is like I2S interface. This part, it's very like based on the domain knowledge, so it might be a little difficult to understand. But yeah, here the bot was not able to retrieve the right information, but this is because the database did not have this data. So like no matter how much you can structure your retrieval and how like well formulate your queries, you could still like not get the right information because like you don't have like the right data to back it up. Right, so if you don't get the right data to back it up, it's still gonna retrieve some close information and it's gonna spit that up, right? But it may not necessarily always be right. So that's when this so there's this other concept called corrective RAG, where basically you add a layer of like evaluator to it to check that whatever information that you retrieve is correct. Right? This is like how standard RAG works. Like whatever question you ask, it will try to retrieve documents close to it. It may not always be right, but that retrieval would obviously affect how the generator would give you your final information, right? So this is how CRAG works. Basically, you retrieve a set of documents. That documents would either be classified as correct, ambiguous, or incorrect using this evaluator, retrieval evaluator. Yeah, so how does that work? Yeah, so basically, there's like a threshold to check whether like the retrieved documents are matching this scoring, like similarity, right? So if it doesn't, if it's above that threshold, then the documents that's retrieved is like considered. And whatever documents are retrieved and considered, those will be decomposed strips to break down that information. And again, once you break down these documents into strips, it will again go back into the retrieval evaluator to filter out like whether all the strips that are broken down is like relevant. And all the relevant information is finally concatenated into this knowledge, this final knowledge strip, which is what we would keep saying. And if it's incorrect, if the scoring is below a certain threshold, then the document that's retrieved is completely disregarded, and it would do like a web search instead. So it would so it does not take those documents into consideration because it's incorrect. So you just do like a web search instead and try to retrieve the information required online. And then whatever you get finally, so that is given to the generator. Just how the algorithm works. And yeah, this is what I talked about. So, and the final thing is ambiguous. So this is when like the score is between like too high and too low, and it's not able to decide whether this information is important. So in that case, it would do both like a web search as well as consider those documents. Yeah, finally, like this is how the evaluation was. So they did performed evaluation on like Chloe, biography, health, and ARC challenge. And they observed that CRAG performed better than RAG in all of these metrics, as well as for self-RAG as well. Self-CRAG also performed like much better than it did, much better than self-RAG. So yeah, overall the retrieval accuracy went up with the help of CRAG. Yeah, that's much.
Do you have any questions for Nura?
Hi, I have a question from online Zoom. I'm just curious about the retrieval evaluator. So how does it know to produce the relevant score? Is it supervisedly trained?
Is it? I'm sorry. How does it know to compute
Yeah.
the score?
Yes, because it's used to evaluate whether the retrieved paragraph is relevant to the query, right? And also to check which paragraph stripped is relevant, right, in order to input to the LM. So how does it know to produce this relevant score?
I think it's mostly a similarity score matching between the query as well as like the document that is retrieved. So like if that is higher than a certain like threshold, that I think we have to define, or like it is. If it's higher than a certain threshold, then it could be correct. Like it could be classified as a correct document. Yeah.
So it's some form of cosine similarity based on embedding.
Some form, yes.
Okay. Oh, okay. Yeah.
The paper itself, so Nura has provided the link on the bottom and corner, which goes to OpenAI. So I see Phong has put his question also in the general chat. Just put the relevant information there. So if you go to section 4.2 in the paper, it does tell you that they're actually using a T5 large model to fine-tune the retrieval evaluator. So it's actually not using for science similarity from what I understand. I'm going to paste the section into the take a look at that when you have time.
I think in the paper, like they do like a bunch of different experiments to see and like compare like which evaluator does better.
Okay, and did they say which one does better?
Is it like their custom evaluator
Okay.
compared to like whatever large language models they
Okay. I'm just curious because if it's pre-trained using some data set, maybe it can face some out of distribution problem. Yeah. I'll take a look at the paper. Thank you.
Yeah, we can continue the discussion on Slack. My understanding is they try to train it fairly general data set. Yeah, there's some details on the appendix D3, but yeah, let's take that on. Other questions?
I have a question. So you know the part that you spoke about, the fine-grained or coarse-grained retrieval, right? Was there any like study done where like as the retrieval becomes more and more fine-grained, how does the performance change of like the correct answers?
That was on the task that you're performing, right? If it's too fine, then you won't be able to retain enough. But if you still need a certain amount of information to recap, like for example, 1 or 2 sentences at least, right? Like if you break it down even more than that, it's not able to like even understand that. Yeah, I'm not sure that regarding this done.
I think maybe just to give some insight, because I'm doing the next week's one. I think that goes a bit more to the granularity of the thing. There are some papers that explore this idea of granularity. It's more of a chunky thing, right? Where they are like, what is the best granularity? And basically what they do is they end up using something that you've heard of, like mixed, if you ever heard of a mixture of experts, these kind of things, they do that with granularity. And then they find that it differs for like different products. So yeah, let's move on.
I just have a small question. For the retrieval evaluator, do you think the reciprocal rank question that you had thought about is that a kind of retrieval evaluator? Or is that like a different?
This is not a retrieval evaluation. This is just to re-rank the document that we have. It's not evaluating the document as such, it's just re-ranking and trying to figure out what is the most relevant document that
Right, and then only the relevant ones get that.
Yeah, I think your point is very useful because there is an evaluation metric that's related to this. It's called MRR, which stands for mean reciprocal rank. And this is used for search engine evaluation. Again, the idea is that you have a list of documents and you think the first document on this is supposedly better because you want to show relevant documents towards the top of the list. So it uses a formula very much like that to say, if you put a relevant document at the top, that's the best. But if you put it at the 10, it's not wrong, but it doesn't carry as much weight, right? So we do this ranking where the first position is rank 1, it's worth 1 over 1. The second position is worth 1/2 because it's rank 1 over. That's why it's called reciprocal rank, right? And let's say you have let's say retrieving 10 documents, and let's say your first document and your 10th document were relevant, but everything else is not. Then you get a sum of 1.1, and you divide by 10, right? You have 10 documents. So your mean reciprocal rank would be 0.11. Does that make sense? So slightly better than just having at the 10. Okay, because the other 8 ranks are all meaningless, they're all wrong, right? So that's one way you can turn something like reciprocal rank into an evaluation. But as Nura points out here, this is for fusion. This is taking several rank lists, also doing them as a reciprocal and adding them together. That's why you have the summation at the beginning, right? So then you can take documents that are in common, several rank lists, and then decide how important they are. Okay. Other questions? Great discussion. Thanks everyone for that. Thank Nura again for her. Okay, our next segment. So Zak is picking the next segment, I think.
So the next section is like the next part of the rank pipeline generation. And I guess it can be broken down into 2 parts, right? Like context curation and the fine tuning of the actual one. So like context curation is motivated because like can't just keep like pre-handling the long context of different documents because eventually like the context length will run out. So that's why you want to like re-rank these results, right? And like pick the top K, the number of like relevant documents, so that your LLM like context length would explode. And then, but the thing is that like even with re-ranking, even we just take the top one document, sometimes that document itself might also be too large for the context length to handle. And so that's when you implement context selection and compression. And the next part is like fine tuning. So like adapting this LLM to specific data formats, for instance, like a JSON format, if you want to like have the LLM only output in JSON for a particular reason, or particular style. Like for instance, like if you want the LLM to be like really aligned to your retriever outputs and be like really robust to their noise, you might want to like do some sort of reinforcement learning to ensure that the distribution is maximized. I think so. I'll be focusing on like this LLM fine tuning part, and I'll be introducing like this new paper that came out on the same topic. Yeah, so this is the existing paradigm, right? So there are two paradigms, right? And the first one is like pre-training an LLM to attend to the content retrieve database. So you can see on the right over here is like this like realm paper from the realm diagram from the realm paper. It basically like masks different tokens, and it uses this neural knowledge retriever to kind of like get a relevant context chunk, and they prepend the context chunk to the query, and they like predict the mask token using just like knowledge augmented encoder. So this was like done back in 2020, so it's really old. But the point is that this was done in the pre-training stage instead of like the latter stages, which is more common nowadays. Yeah. So the issue with this is that it's really computationally expensive or to train LLMs in this manner. But I guess it's more robust noise as well. And this is the second paradigm, right? So this is like the replug realm paradigm. So it just concatenates the retrieve outputs in the LLM. So for instance, in this like diagram over here by replug, you can see that the context is jobs to CEO or, and the retrieve document is jobs co-founder Apple and his parents corrupt, right? So what they would do is like they would just like prepend the context of this retrieve document to a test context, and they will use the LLM to like output the final answer. But the thing is that the LLM is not like might not be trained to use the retrieve outputs because the LLM in this case is frozen, and the only thing that's trainable is actually the retriever, as well as like just a retriever. Yeah. So in this case, it might not actually be really fast and noisy input. So what I mean by this is that, like for instance, if a retrieve document is wrong, your LLM might just like blindly refer to the retrieve document instead of actually following its own parametric knowledge. Yeah. So the question is then, can we fine-tune realms such that the LLM can be more robust to noisy inputs, and the retriever can retrieve sources that align with what the LLM needs? Yeah, so this is where RADIT comes into play, and it kind of like tries to address these two problems. Okay, so this is the general big pipeline of what RADIT does. So let's really break it down, right? So first you have the user input, then you have the retrieve documents, C1 and C2. So you prepend the documents in parallel to the query. So it is done in 1 and 2 over here, and you feed them like in parallel in separate like queries to the LLM, right? So this is pretty standard so far. But now instead of like any other kind of loss functions or something like that, you actually take you actually have a ground truth table. It's like the actual answer given your query, like without a context, right? So the LLM is actually trained to like essentially give the same like ground truth table no matter your context, right? And you might be asking like why the authors do this, right? Because essentially you are trying to like make the LLM robust against noisy inputs. Yeah. So because of this like training styles, the LLM like does predict the correct tags and ignore the noisy input. You can see over here that this is a negative logarithm loss of the LLM, and Y is the ground truth table. C and X are the context and the query response. So the circle in the middle just means that it's concatenated together. Yeah. Yeah, so it just uses like a very simple mixed token prediction method. But it gives you're training the LLM to like give you the same like ground truth table, like no matter your context. Yeah. Okay, so now let's move to like the next part of the pipeline, right? So it's your retrieval fine tuning. And like what you want to answer is if the retrieve text message enables the language model to generate a higher score, you want that text message, the retrieve context chunk, to have higher like relevant score, I guess. Yeah. So for Reddit, they use this like PRs to measure how they want to like measure like the relevance of that context chunk given in order to produce a certain like a ground truth table. Yeah. So you can see here that PLM is just the probability of a language model outputting the ground truth table given your context chunk and your query. What you're doing over here is that you are just trying to normalize over all the top tier context chunks, such that you can get like a nice distribution that integrates one, right? And you can see that they approximate these two equations together. If you look really carefully, the only change is that it's in like the C, right? Instead of like C becomes C prime. So like what I'm trying to say is that they approximate like the top tier context chunks with a probability that equals one, and therefore they can do this normalization better. Yeah. You also notice that they have a temperature tau as a hyperparameter. So when you divide all these like different probabilities by tau, if like for instance, like if your PRM is like originally one, and another PRM is originally 2, right? If you divide it by tau, which is equals 1, you just get 1 and 2. But if you divide it by like 0.5, you get like 2 and you get like 4, right? So because you are trying to take the exponent of these probabilities, like this exponent would like increase if the difference between the two numbers, the normalized exponent will increase if the difference between the two numbers are much greater. So basically, it determines how peaky the probability distribution is, and a more peaky distribution will mean that you can have more aggressive fine tuning to retrieve the specific context. It means that for any advantage that looks like your ideal context, you want to retrieve the specific context. Yeah. Okay. So if we go back to like this part over here, right, you can see that you actually try to minimize the PR divergence between your PR as well as like your PRM, the PRSL. Yeah. So what this does is basically it's trying to minimize like the distribution. It's trying to get the retriever to like retrieve passages that are more effective in using the correct answer. Because sorry, the PR is calculated over here. So in this calculation is S is taking a dot product between X and C. So you can think of it as in terms of like it's normalizing over the similarity scores between the query and the context chunk. So by taking the PR divergence over here, you're trying to like you're trying to align what the language model needs with what the retriever retrieves. Yeah. Yeah, and so this is the general pipeline. First you have your contacts that you retrieve, and then you pass these two contacts prepended to the query into the LLM. And you train using like the ground truth table that you already have, and then you kind of like propagate this loss of the LLM into the retriever so that your retriever retrieves the stuff that your LLM needs. Yeah. And empirically, this paper presents like really good results. It has a higher score on the multiple benchmarks. And so I think the main takeaway here is that like by integrating like the loss in the LLM into the retriever, you can kind of like bind the two together. And so you get a better model overall that retrieves what you need. Yeah. Yeah, so that's all. Thank you.
Thank our speaker. Any questions? You saw put a post on Slack about MRR. We had a short discussion about the page with the ask. Manas, sorry, Manas has so I think this is a nice diagram. So you see two different components, right? Zach said you need to learn what to retrieve. right? That's the RMT. And then you need to make sure that what you retrieve is useful to create the actual output, which is on the right side. Right? So you have two different parts to optimize, and then you're doing the Zak explained already in the purple part, the KL divergence to make sure that these two things are coupled well, right? They're doing things that are gonna help each other out. Do we all understand why on the right hand side the Y looks the same? Can anyone explain? Yes. So that's the gold label, right? So that's what we're trying to train the retriever pipeline to generate. Right, so it's got to be the same for whatever is output with whatever chunk that's being retrieved, right? They're trying to do this through the supervised fine-tuning process. That's why the Y is constant. Other questions? Any comments online?
This is Haito online. Thank you very much. So my question is, I'd like to know what type of representation, I mean, the way of injection, like, for example, for this current method, RADIT, for the retrieved results, are they injected as text or embedding vectors into the LM generation process?
So very good.
I mean, how are the retrieved results injected?
Oh, it's just as a text. Yeah. So as you compare the dot product similarity between your query and your context chunks, but your context chunks are passed to the LM as text. Yeah.
So do you mean the raw text are used or embedding vectors?
Or as in like being passed to the LM.
Yes.
But yeah, it's a text.
Raw text, right?
Just text. Yes.
Okay, thank you.
Yeah, I think Zach is right. You know, they're saying they're fine-tuning using the next token prediction objective, so it's probably, as I've said, to the raw text, not using the embedding. I mean, that would be very interesting to see whether an embedding-based approach would also give you good results. Right, but I think they're trying to guide the generation one at a time, so they need to do next token prediction. I mean, if you wanted to evaluate the entire output, maybe it's fine to do it at the end using a vector-based embedding of the entire output, but they still have to guide the elements to generate the tokens, right? Yeah, so probably the next token prediction is the correct way to
But by the way, I mean, I checked the entire slides for this lecture this time. So as a complementary comment, I'd like to say that for the way of injection, as far as I know, there can be 3 types of ways for injecting the result, for injecting the retrieved results. For example, the current example is using the raw text. There can be another 2 ways. One is using embedding vectors. The third can be parameters like LoRa. So later I will share the detailed descriptions within the Slack channel. Thank you very much.
Thanks for that highlight. So that's a good thing for our scribes now that there are, or at least potentially 3 different ways to inject information coming from the labels. Okay, why don't we take a 3-minute break and we'll come back to section 4, 5, and 6. I think Haitao and I have a couple announcements to make by then. So have a 3-minute break if you need the restroom or anything. And Ruiwen will take.
Yeah.
Yeah. No. Yeah.
Okay, everyone, I just wanted to give you a couple of quick announcements. So, over the last week or so, I tried to go into everyone's projects to give comments for those of you who did, your second sprint, update. So, now I think it's close to the time where you need to make sure that your numbers, in the worksheet are updated for project. So make sure you go to the project page, this page, and then go all the way over. Okay, and double check that this column, weeks 5 through 7, has been updated with your actual amount of time that you spent on your project. I see some of you are on it now. That's very updated. Okay. If you've already done your lecturer roles, or the support roles, or PTOP A and B, or if you're a 6101 PhD student, you need to fill in your hours for this and this. If you're doing B, then of course in the second half of the semester starts today, you will need your lecture hours for your second assignment and your support role, your second one. And you'll start working on your project hours for the. Okay. So again, the total is what we need to look at, okay, which is that for 6101 students and CP 3108A, you need a total of 7 here by the end of the semester, and a total of 130 by the end of your each. Okay. If you're external, of course, you don't have any of these requirements, but people continue to do their projects around. Okay. On the projects channel, all of you should look through the pins. Okay, the pins have a 1 or a 2 or both if I've commented on them. So again, you can just as you start to do sprint 3, which is starting this week. Okay, you need 2 weeks to get to the end speed. Sprint 3, which is week 9 in the US, today's week 7. Then you should go create your next bookmark. Okay, you you can look at, for example, square 3, and then take any slides you see here that you don't have in your current deck, and just add it to your current deck. Okay, and then just tell me by adding a host to your thread. Okay, so you click on any of these threads. Okay, and then look at they're all revised, and then you can just add a post at the bottom, say I finished my script, and hide out, and then look at it. Yeah, and then we'll try to give you some comments. All right, so it's very important that you have enough hands-on time frame, and it's this point, like I said in the channel, that people start to drop off in the class because they have a lot of assignments. Okay, that is a reality because this course doesn't assign you very structured information. Okay, this sprint starts to help you give some structure. That's all. Okay, but you know, there are certain repercussions if you drop the course. And we want you to abide by the honor system. And when you put the hours in the columns towards the end of the worksheet, please own up to it. If you haven't done it, it's okay. Work with us. Prescribe other things to help out. Okay. So for example, those of you who are doing 3208B and don't have enough hours yet, I would suggest that you go through the pinned projects here and look through the other projects and give comments to others. And even if you're not sure, maybe you can just do a little research work, ask GPT, or ask for relevant documents and then comment. Okay, so again, especially for P2AD students, that's very the other thing that I'm going to bring out is something that I talked with Haikao about. So Haikao and I are thinking of actually taking the notes that we are compiling for the scribes and actually compiling it into a survey of sorts meant for a Retrieval Augmented course. Okay, so it's not approved yet. We actually haven't sought the approval of SOC yet, but it's possible within the next couple of weeks we'll get approval. That our CS6201 course, information retrieval course, will be updated a lot from this course. Okay, so what this means is this is sort of like our startup course. So like we get seed funding, we get everyone to do this project, and then we actually launch the actual course, and you guys are helping us do that. So first, thanks to all of you for participating in this course. Making changes coming up. That's exciting. The other part of it is, of course, Haikao and I would like to give thanks to you for helping with this course. And we will be, I think, coming to you to ask you for how you can contribute for the actual article that Haikao and I will prepare based on the notes that are used. Okay. So if you're, I think Haikao and I will write on the general channel how you can get credit for that. Okay, so we'll acknowledge the course in general, but if you would like some higher form of acknowledgement, then we will try to draft out what the deliverables are, so that anyone who has more time and would like to see their contributions as pay more dividends can do so. So Haikao, you're online, so maybe say a couple words as well.
Yeah, thank you very much. Yeah, mostly like that. So I wish I can be helpful. Yeah, provide some helpful feedbacks. Yeah, thank you so much.
Okay, so currently there are myself, Haikao, and Isong, and one other PhD student of my group are likely to participate in this. But again, we will come back to you with more instructions as the course goes on. Okay, because AI is moving so fast, we feel that more courses like this one are going to come out of SOC, and that it will come and retrofit other courses that we have that are existing. So I'll let you know more as we go along. There are certain plans that management has for how certain courses are run. but especially those of you who are sort of self-selected to be part of this experiment, if you know of trends that you see that you think association teaching, come and talk to me. You can write on the general channel, oh, we know more about RL or other things of that sort as an undergraduate or as we need more hands-on or things of the sort. There's been talk at the Stanford course about LLMs from scratch. That would be a very interesting course to have at NUS. In fact, we have all the bits and pieces. It's just not cobbled together in a way that's sort of like easily to use. Okay, so that's all I have for that.
I just made a comment.
Yes, go ahead, Jay.
I noticed that for this course, we haven't really gone so much into the authentic part side of things. And agents really big part of here in development space. I was sort of wondering, I was thinking, speculating that maybe the next iteration of this course there would be more sort of agentic drag material.
Yeah, I think agents are getting crazy busy. I mean, they can multiply themselves and they can make us infinitely busy. That's not a problem. So there's a lot of work going on there. So I think our research teams at NUS are also very. So that's a very. Any other comments? Any comments online? I don't know. Whenever I look for a comment online, I look at. Okay, let's have Ruiwen come up for the next part.
Hi everyone. Today I'm going to talk about augmentation process in web. And first, let's discuss why do we need augmentation. As we have seen from previous lectures, the vanilla one-time drag performs quite well in many scenarios. But for complex reasoning and agentic tasks, the vanilla one-time drag may not be enough complex, and it can hardly solve multi-stack or open-ended tasks, as it provides insufficient tasks when the contexts are dynamically updated. So we want more control and better depth from retrieval, and we also want dynamic context updates. So this is why we need augmentation in graph process. And today I will introduce 3 categories of different augmentation methods in graph. The first category is iterative retrieval, which will alternate between retrieval and augmentation until some kind of converged condition. And the second category is recursive retrieval, which will continuously update the query and also decompose the problem until some kind of convergence criteria. And the final category is adaptive retrieval, which decides when to retrieve external knowledge, what to retrieve, and when to stop. And I will introduce these 3 categories with one example for each category. Let's first talk about iterative retrieval. I will introduce an example, a typical method for iterative retrieval generation here. Formally, given a question and a retrieval corpus where the elements of the corpus are paragraphs, this method will the following process for T iterations. We will first leverage the previous generation from LLM called YT-1, concatenate it with the original query queue to retrieve the top 10 paragraphs. And then with the retrieved top 10 paragraphs, we will prompt an LLM to produce a new output YT with both the retrieved paragraph and also the query queue as the query for the next retrieval. So it is quite simple. It just alternate between retrieval augmented generation and generation augmented retrieval. And this is an example of how this method works. You can see that we have the original question as the queue here. What is the date of player who won the 2015 Agarwal Rising Star Award? We use this query. We use this question as the query to retrieve the first similar document. As we have k equals to 1 here, we retrieve the top 1 paragraph. see as the EQ, and we use Q and EQ as the input to prompt LLM to generate YY. And then we use Q and YY to do another retrieval and get a new retrieval results as the context for generating Y2. And we will repeat such process at T maximum times until it reaches an answer or reaches the maximum step. Next, we will talk about recursive retrieval, and I will introduce IRCO as an example. From its name, you can very easily imagine that this method will iterate the COT listening process with document retrieval. So at each retrieve step, this method will use the last COT sentence generated by an LLM as the query to retrieve key documents. And these key documents will all be added to a document collection. And then for each reset step, the LLM will generate the next COT sentence with the query and all so far accumulated documents. So if we are at timestamp T, we will have like T times K accumulated documents all as new context, not only K documents. And finally, when this iteration reaches its end, we will use a QA reader, which may be the same LLM or another LLM, to take all accumulated documents as the context together with the query, together with the question, and then that's another repeat of COT reasoning to obtain the answer. And here I also provide an example of how this method works. You see with the original question field, it can retrieve the first collection of documents, as you see in the as you see in here, this yellow or orange one. And with the original question and this yellow document collection, we will produce the first COT sentence one with an LLM. And then this T1 will be used as a query to retrieve the next key documents and in the blue collection here. And then when we are generating the T2 in the second synthesis of the COT listing process, we will use both the original documents and the blue documents. So we will repeat this process until it reaches its ending criterion. And then we may have many documents here, like the orange one, blue one, and green one. And we will use all of these documents to conduct another COT process to get a final answer. Okay, and then we will talk about the final category, which is adaptive retrieval. And I'd like to introduce a typical method called FLAIR here. This FLAIR method adaptively decides when to retrieve external knowledge according to the uncertainty of LLM generation. When it will detect the probability of, it will examine the probability of generated tokens every time a complete sentence is generated. And when it finds like the probability of some generated tokens is lower than a threshold, author will use two ways to create a retrieval query with such low confidence tokens. The implicit way is just using this new sentences while masking all these low confidence tokens that they can very quickly wrong generations. And they also propose an explicit way of creating a query, which is prompting the LLM to generate a question of which the answer should be this low confidence tokens. And then once we have the retrieved documents, we will integrate them into the context and add future generations. This is the example from the FLAIR paper. That's the figure 1. In the step 2, you see these two underlying spans of tokens, and the University of Pennsylvania and a law degree. This underlying parts indicates low confidence tokens that has the probability lower than the predefined threshold. So when FLAIR detects such tokens, it will create a query as shown in figure 3. The implicit query will be created just using the original sentence with this low confidence tokens masked with special tokens. And the explicit query will be generated by prompting another LLM to ask a question like to which the answer is University of Pennsylvania or a law degree. and you see it will generate some kind of queries in the green box. And we use this either kind of query to retrieve from the document collection, and we will have some additional information. And then after adding this additional information, the LM will like repeat its generation process starting from S1, and it will generate like graduate from the University of Delaware, etc., which aligns with the factual information in the real world with such additional information. So to summarize, I covered 3 types of augmentation process in graph. The first type is iterative retrieval, which automates retrieval and generation. And I introduced the iterative retrieval generation method. And the second type is recursive retrieval, which gradually refines the query and decomposes the overall problem into subproblems. And the typical method in this type is the IRC method. And finally, we talk about adaptive retrieval, which decides when to retrieve external knowledge, what to retrieve, and when to stop. And I use the FLAIR method as an example. And nowadays, as the fundamental capabilities of language models are growing very rapidly, you see many different adaptive retrieval methods. They are very simple, they are strong, like the SearchR1 method, just using special tokens and reinforcement learning produced in previous lectures. So I think it will also be beneficial to know those methods who are interested. And what I discussed today, I think might be very relevant to what presenters from WING.NUS will discuss. So I hope I will give you an introduction about what this augmentation method is like. No more in later lectures. Okay, so that's all I want to share today. Thank you very much. Question?
Any comments? So Ruiwen went quite straightforward between iterative, then recursive, then finally adaptive. And so he's presented fairly basic models for each of the types. They're sort of like prototypes of how the more advanced methods work.
I'm just curious, was there any like comparison between the 3 that was ever done? Like on this, maybe like on the same like benchmarks.
Oh, you mean like comparing all this method on the same benchmark?
Yeah, I mean, especially kind of curious, like between the iterative and the recursive, like retrieval, the augmentation, right? Like how, yeah, I don't know how that would like affect.
Actually, I think some recent benchmark, maybe in the recent 1 or 2 years, will compare a lot of such methods, but unfortunately, I'm not very familiar with all results. And I think the most popular and strong method among these 3 should be that retrieval, because it provides more freedom to the retrieval and maybe the language model framework. So yeah, that's kind of answer to this.
Sorry, maybe another answer to this question is that based on the publication year of each shown method, for example, I think for the previously published method, it will be used as a baseline and will be improved. That's a quick answer from my view. If you want to make a comparison.
Later methods would be previous method as baseline and those stronger performances.
Okay, let's thank our speaker, Ruiwen, again. So Barid, are you online?
Yes, I'm online. Yeah, I'm ready.
I will stop the screen share. Let's see.
Okay. Okay, so is it visible?
Yes.
Okay, so yeah, let me start. So So in the next like 15 minutes, I'm going to discuss the RAG evaluation. So I think so for all the systems, we want to evaluate the performance. We need to understand the behavior of the system. So in this topic, so we try to evaluate our RAG system. So in the last like a few weeks, so we already see this orchestration a lot. But if we zoom out a bit, we see at least say several black box. The first black box maybe is a retrieval. So in this black box, we have the vector store, we have our retrieval algorithms, and then we feed our input user input to this component in this into this black box, and we get the relevant information. Second black box is our generation black box. So we have a large model in it, and we want to use our retrieval information to guide our large model, and they work together in this black box. So you see the large RAG system is not like a typical end-to-end system. So it has a multiple stage pipeline. So which means that failure can happen at each stage. So in this case, so when we try to evaluate a RAG system, so it's a quite different from we evaluating a larger models. So in that case, we need to evaluate each black box, each component individually. So in this case, in this topic, we try to discuss how we can evaluate the retrieval component and how we can evaluate the generation component. And finally, we also try to give some advice to like evaluate the RG system as a whole. And in that case, we take the end-to-end user experience into account. So please note that. So in this topic, so we always assume our vector store is perfect. So which means that our retrieval component can provide sufficient information to guide our larger model, and we believe we can always find relevant information in our vector store. So we have 3 evaluation goals. The first one is we needed to make sure that our output, the answer is correct. So this is an end-to-end task. Second goal is so we want to understand if all our output, our answer is granted in our retrieval documents, because we believe this is a good way to prevent hallucinations. And we all see lots of these problems in larger models. That's why we think about RG as a solution. So right. And the third goal is trying to understand the system behavior. So in that case, we think about we try to figure out how we can optimize the performance. So we ask the question: is this a problem from our retrieval component? Is this just a problem from the generation or the larger model? So let's start from the retrieval evaluation. So in this evaluation, we have 2 goals. The first one is the correctness. We want to get the right context or right documents for the input query and to support the larger model to get the right answers. And the second one is the relevance. So in some cases, so we say we retrieve lots of documents, but they are not relevant to our input query or our final answer. So in that case, we still believe this is a bad retrieval components or black box, right? So suppose we have the ground truth document for each task or query. So in that case, we want to want to know if our retrieval documents hit the target. So you can imagine that in this is a kind of like a classification problem. So we in that case, we can leverage so many like supervised learning metrics for this. So like, for example, we can use accuracy, processing, and recall. And I believe we already see this a lot in our machine learning textbook. So, but we say this is kind of like a problem, because in practice, so these metrics don't take into orders or rankings into account. So in practice, for some like let's say we can retrieve so many documents from the internet, but we only want the first 5. So in that case, maybe this matrix can, from this matrix, we can see we already hit our target documents, but we don't know if we just get the top 5 things, it still works. So in that case, we think about some kind of like a ranking matrix, and we see this ranking matrix are from the information retrieval field. So for example, the first metric, so MMR, it considers the rankings of each document. So for example here, so we say if this document is at the first place, and then we say this is a good retrieval black box or component here. And but in practice, yes, we still think about this as another scenarios where we don't have the ground truth documents. So in that case, so we think about let's consider the if all the retrieval documents are relevant to our input query. So in that case, probably we can hire some people to annotate all the data set, all our retrieval documents. So actually, it's probably you will believe this is taxing, but it potentially aligns with human judgments. We see so like many high technical companies like Google use these strategies to evaluate the system. But for our so if we can't hire people, yes, we can hire our large language models. So we can still try to craft some like prompt, or try to to judge our to judge the relevance between our retrieval documents and the input query. So for example, so we can directly ask the model to judge if the context or the retrieved documents are relevant to the query. So and also we can try to annotate a handful of examples like on the left side, and try to format all these examples into our prompts, and then we can do ICL in the context learning. And we say this is a good place. This is a good way to improve our judgment. And then we go to the generation. So compared to our retrieval evaluation, so we should know there is one additional metric here. So that is the faithfulness. So recall that when we think about the RG model, we believe that this is a way to prevent hallucination, right? To prevent hallucinations, we want our answers are granted in the documents or some verified documents. So in this case, in our RG paradigm, so we say we want all our answers are granted in the verified documents from on the external base or from the internet. So in that case, we can think about like three metrics in our generation evaluation. So first, we still think about the scenario that we have the ground truth documents. So the case is very simple. So because our documents and our inputs or the outputs are sentence, we can use sentence transformer to measure the semantic similarity for them. So for example, in this case, we can hire sentence birds, and we can concatenate our answer and the multi output into one input, into one prompt, and then we send this to the sentence bird, and the sentence bird will give us the relevance score. Similarly, we can concatenate the documents and the output and send them to the sentence bird, and then we get the faithfulness score. So you see, this is a very simple way, but in practice, I believe this the performance is very well. Secondly, yes, we can still use our large language model. I guess this is kind of like a more popular way. So in this case, we can similar to our retrieval retrieval evaluation, we can create some prompts. So for example, we can ask the model trying to judge if the pairs, if our output and the answer are like a semantically aligned with each other. And similarly, we can still use the ICL style for this, and we can create some demonstrations, and we chain all the demonstrations into our prompt and try to instruct the model to judge to judge and give the evaluation score. So this is the case where we have the ground truth documents, but in more like generally, so we don't have the ground truth documents. So in that case, we think about this recent work called RAGAS, and this framework is I think they borrow idea from the factor school paper, They try to break down all the try to break down the retrieval documents and try to do some reverse engineering work and see if this pipeline can use to evaluate the generation process. So what do they do? So first, for the faceless score, they ask the larger model to give some to generate some statements for the question and answer. So they will get like a V statements, and then they input all the statements to another larger model, use a large model to judge if all these statements are true for the answer and the query. And then they get the S verified statements. And finally, the faithfulness scores. Oh, sorry, this should be S divided by V. So the final faithfulness score is S divided by F. So I guess this is a very good way, because we don't have to use the like ground truth documents. And secondly, we can think about the answer relevance. So similarly, we can ask the model, we can ask a larger model to generate a question for the answer of our RG system. And then we concatenate our question, a generated question with the original question, and then we send them to the sentence part, similar to our to the case where we have the ground truth documents, right? So, and then we get the relevance score. And lastly, so in this paper, they still propose that we can think about the context relevance, because like I said, in some cases, we can retrieve lots of documents, but some of these documents are not relevant to our input or output. So in that case, we still say this is a bad generation component or retrieval component. So in that case, they propose to consider the context relevance. So in that case, so we ask the larger model to extract useful to extract all the useful sentences that are relevant to our query from the original retrieved documents. And then we try to evaluate all these retrieved documents with the total number of the documents we have got, right? So that's another way to think about the context of relevance. So we say if this score, like the CR score, is 0, which means that we have a perfectly we have a perfect set of retrieved documents, because all the documents are relevant to the query and the answers. So that's the idea of this. And the final one is the practice for the, so I should say this is kind of like a semi-automatic RAG evaluation pipeline. So in our in my discussing, so you say, so the best practice for this might be, so you can annotate a bunch of data set. So first, you can think about the you define the criteria. So for example, you want to know the faithfulness, you want to know the relevance. And second one is you try to annotate a handful of examples, and then you think about your prompt, and then you try to chain all your data set or examples into your prompt, and then you instruct a large model to give the final judgment. So in this case, we say this is the best way, because in many RAG scenario, so we don't have the ground truth documents, and this can alleviate all the pains here. And lastly, so we say we can still think about the taking into the end-to-end user experience into account. We say the large models is some kind of like a more powerful. Our RAG system is a more powerful large models, and we can still share some metrics with large models. For example, we need to evaluate the efficiency of the larger model. So here we think about the latency. So we will say, so if when we use large models or RAG systems, so the system can respond very quickly. And in this case, we may put this latency into account. And we also think about the diversity. So this is another important problem. So because when we input the same query to our RAG system, probably the system may multiple times, probably the system will give different answers. So in that case, we say the system is not self-constant. So we still need to understand this behavior of our RAG system. And also we see some other robustness problem, like how about we input some jailbreak prompts into the model, and say if we can break down our RAG system. And all these metrics, again, shared with the larger models. So we are not going to go through all the details here. So that's so I'll stop here. So finally, I think so all the RAG system, RAG evaluation is about the engineering. So the best practice is we can go to some like tutorial. So for example, I guess this is a good one. And then is about the evaluation tools. So I recommend this Haystack. So I use it a lot, and I find it's very important. It's very easy to use, and it has a clear pipeline for evaluation. And I guess it also has a user-friendly interface. So thank you. So that's all my presentation. So any question?
Time for our speaker first. Have any questions for Barid? Okay, yeah, Barid highlighted this last comment about evaluation tools. So definitely for all of us doing projects, you need some form of evaluation. So if you haven't had a chance to look at Haystack, or you can share your notes about evaluation tools generally on the project channel or on the resource channel. There's a separate channel. So as we head towards the second half of the semester, you're supposed to get your hands in. So make sure you spend it. I've allocated a sufficient amount of time to look at evaluation. Okay. And I just checked whether our last presenter is online. I didn't.
Yes, Rob.
Okay,
I'm there.
that's right here. Okay, great. So, Sahej, you can share your screen for your final segment.
Just a second. Okay, just a second. Nura, just a second, bro. For some reason, Just a second. Some issue with your screen share. Just a second. Uh,
You're having problems with screen share.
yeah. Is my screen visible?
Not yet,
It's not visible.
not yet.
Not yet.
Wait, share screen.
Sometimes if there's problems with the screen share, you need to shut down Zoom and then jump back into the session. That sometimes helps.
Okay, is it now visible?
Nope,
Okay, I'll just rejoin.
yeah, drop the Zoom and come back in. But just to note also that in SOC, now it's the time of the year to start bidding for projects for final year project students as well as undergraduate research opportunities for year 2 years of students. So there are many projects.
Hello, is my screen visible now?
Yes.
Okay.
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 So I think go ahead and start.
So I'll try to keep myself a bit brief since we are already running a bit late. So I'll speak about a few future prospects of RAG as a whole. The next slide. Okay. So I mainly focus my work towards a lot of review papers as they summarize a lot of what is going on towards research directions at the time. So apart from pure research, a lot of the work has been going towards adapting RAG towards particular case scenarios. A lot of them have been towards fact-checking conversational agents, low resource question answering, real-time assessments, and enterprise-related search. This has been possible mainly due to the advancements in recent years, where we have slowly moved towards multimodal RAG, graph, and are slowly making our way towards agentic RAG. A lot of the problems are currently being dealt with, such as hallucination in RAG, the long document lengths, and of course, retrieval of slightly incorrect documents that may cause issues in the RAG systems. So one of the key things that's interested me was agentic RAG, and I remember somebody during the Q&A session speaking about it. So I'll touch a bit about agentic RAG. So I found another review paper about agentic RAG, which essentially uses not just a single LLM model, but multiple combinations of models to enhance the retrieved documents. It enables us to combine more complex data and has the ability to deliver much better results as compared to a typical RAG system such as knowledge RAG or simple other RAG methods. So in an agentic RAG system, the main model is used as a controller for a small agent or a group of agents that retrieve different parts or different information essentially from document. They can include small agents like Google search, uh, uh, Google search, graph rag, and essentially going through a lot more amount of documents than a typical RAG pipeline is able to do. There are multiple methods that have been seen such as prompt chaining, uh, prompt summarization, aggregation, orchestration, and synthesization, and feedback and review methods that are used to enhance these type of pipelines for better quality of results. Again, in most scenarios, the agentic system has to be specifically curated towards addressing the needs of the rack system and the potential application that it is being made for. Some potential issues in this type of scenario can be the very high requirement of compute, as instead of running a single model, multiple models are run. It can also lead to a more complex pipeline that is difficult to enhance and possibly debug, and can also give potential issues towards scaling of the pipeline. Now I would like to open to questions. Sorry again, I tried to be a bit brief in order to save time.
Okay, let's thank Sahej for his first statement. Any comment? So if you look at this paper, there is a GitHub repo connected to it, but there's actually not that much. I mean, look through their points. They cover very much what we are already covered in this lecture. It's just that you can support several LLM models for it. So actually, there's a lot more that if we try as a class or if your project want to go deeper in this direction, and you want to try to specify what are the agentic goals that are necessary for getting better results within a particular domain, that can be very effective. Okay, but a lot of times these pipelines come up because people have thought about them within particular domains, and then they try to generalize out of it. Okay, so for example, thinking about multi-agent RAG overall is a little bit too abstract to come up with goals. But if you say, I want to do RAG for a particular domain, for example, for troubleshooting maintenance of appliances, or for diagnosing dosage requirements for medicine, or how to study for a RAG course. Okay, then because you've made them more specific in instantiation, it'll be easier for you to come up with particular model architectures or prompts that would be useful. For example, just on the fly, let's think about a RAG course, right? If you're trying to build an agent to help you study for a RAG course, like what kind of agents would you want to have in the multi-agent RAG? One to give you lecture slides, one to help you scribe, one to help you build Kahoots, right? All the things that we're doing in this course, right? So are there other things that you would need to do, like to do come up with projects, create projects to give you ideas for the needs, right? So how would you do that? So that's sort of like the agentic framework. It's easier if you try to go down one level and then come back up, right? So you can say, okay, if I did it for a RAG course, is it the same if I'm studying computer science? Or is it the same if I study, let's say, a primary school course, right, compared to a tertiary? You can try to bring it up level. So I think that's some of the frontier of what we're going with agentic RAG that both Sahej and JF. You want to see that development. It helps to try to do it ourselves. Can't wait for surveys to come out. So let's thank all of our speakers again for today. And so that's it for today. So we'll see you all next week, same time, same place. Thank you, everyone.
Thank you.